In this video, we're going to study the four most important properties that a relation can have. So let's start by talking through the definitions of those properties. We start with a relation on a set X, and the relation is written as tilde, as usual. And the first property is called reflexivity. We're going to write R for short for this property. So a relation tilde is called reflexive if and only if every element of the set is related to itself under this relation. The next property is called symmetry, S for short. And a relation is called symmetric if whenever you have X is related to Y, then also Y must be related to X. Okay, there are no hidden assumptions here. This means always, if X is related to Y, then Y must be related to X as well. Whether X and Y are different, whether they're the same, if a relation is going to be symmetric, then whenever X is related to Y, Y must be related to X. Third property is transitivity. A relation is transitive if and only if whenever you have X related to Y and Y related to Z, then it must be that X is related to Z. And again, there's no hidden assumptions here. There's nothing that I'm not telling you. This must be true for absolutely all X and Y and Z, whether they're all equal, all different, whatever. If X is related to Y and Y is related to Z, then X must be related to Z in order for this relation to possess the transitive property. So finally, the property of being an equivalence relation is just that the relation should possess all three properties of reflexivity, symmetry, and transitivity. So a relation is an equivalence relation if and only if it has property R, property S, and property T. Let's now investigate some familiar relations to us to see which of those properties they've got. I've drawn a table at the bottom there with a column for R for reflexive, S for symmetric, T for transitive, and E for equivalence relation. And we're going to go through some familiar relations and decide which of those properties they have. So we'll begin with the relation less than or equal to on the set of real numbers. So you at this point should pause the video and try and decide for yourself whether the less than or equal to relation on the real numbers has each of those four properties R, S, T, and equivalence relation. Okay, let's work through then reflexivity. So is this relation reflexive? Well, I have to decide for each real number X, is it the case that X is less than or equal to X? Of course, the answer is yes. X is less than or equal to X for all X in R. So, yes. So let's have, let's write it like this in capital letters. Okay, next, symmetry. So, to check whether this relation is symmetric, we need to know if whenever X is related to Y, is it necessarily true that Y is related to X? And of course the answer is no. 1 is less than or equal to 2, that's true, but 2 is not less than or equal to 1. So this time the answer is no, it's not symmetric. On the other hand, less than or equal to is transitive. So it's a standard property of the less than or equal to relation that if X is less than or equal to Y is less than or equal to Z for real numbers X and Y and Z, then it's certainly true that X is less than or equal to Z. So yes, less than or equal to is a transitive relation on the set of real numbers. Finally, if we look at E for equivalence relation, well, the answer here is no, because to be an equivalence relation, you've got to have all three properties R, S, and T, but it didn't have property S. Okay, next example, let's move on and do the example of less than on R. So less than is a relation on R. It's not reflexive. It's not reflexive because 0 is not less than 0, for example. So no, this is not a reflexive relation. And it's also not symmetric for the same reason that less than or equal to was not symmetric. 1 is less than 2, but 2 is not less than 1. Finally, less than is a transitive relation, and again this is just a standard property of the less than relation on the real numbers. If x is less than y is less than z, then x is less than z. So yes, the less than relation on the real numbers is transitive. And again, finally, in the last column, it's not an equivalence relation, because to be an equivalence relation, you must have all three of the properties R, S, and T, and this doesn't have property R. Okay, let's now try a different relation. Let's look for one that's, well, slightly different. So this time we're going to take the relation less than, sorry, not equal to, on the set of natural numbers. So again, pause the video and decide for yourself, do you think the not equal to relation is reflexive, symmetric, transitive, or an equivalence relation? All right, well, it's not reflexive, and the reason is that, for example, 0 not equal to 0 is false. 0 is not related to 0 under this relation, so the answer is no, it's not reflexive. On the other hand, it is a symmetric relation, because if x is not equal to y, then also y is not equal to x. So not equal to is symmetric. And finally, transitivity. Well, this relation is not transitive because 1 is not equal to 2, 2 is not equal to 1, but it's not the case that 1 is not equal to 1. So, but this is false. So no, the not equal to relation is not transitive, at least not on the set of natural numbers. So again, we do not have an equivalence relation, because to be an equivalence relation you must have all three properties R, S, and T. Alright then, final example. Let's look at a congruence example. So we're going to take the relation of congruence mod 2, and that's a relation on the set of integers. And you'll remember that we say that two integers x and y are congruent mod 2, and we write x triple equals y mod 2 like this, if and only if x minus y is divisible by 2, so x minus y is even. Well, is it reflexive? Again, you should pause the video and decide for yourself whether this relation is reflexive, symmetric, or transitive. And now I'm assuming that you've done that. So the answer for reflexivity is yes, it is reflexive. So for any x, an integer, x minus x is 0, and that is divisible by 2. So it's true that x is congruent to x mod 2, and that means this relation is reflexive. So let's put a big green tick to indicate that. Okay, next, is it symmetric? Again, the answer is yes. And the reason for that is if x is related to y under this relation, well then x minus y is a multiple of 2. So let's say 2 times k, where k is an integer. Well, in that case, y minus x is 2 times minus k. So if x is related to y under the relation of congruence modulo 2, then y is also related to x, because y minus x is also a multiple of 2. So we've shown if x is congruent to y mod 2, then y is congruent to x mod 2, no matter what x and y are. So this is a symmetric relation. And finally, for transitivity, if x is congruent to y mod 2 and y is congruent to z mod 2, well, let's come and write up at the top here. Let's just do a little bit of arithmetic at the top here. We're assuming x is congruent to y mod 2. So that means that x minus y is equal to 2 times k for some integer k. And similarly, we're assuming y is congruent to z mod 2. So that means that y minus z is also an even number. It's also divisible by 2. So let's say 2 times m. So I want to know, is x related to z? And to figure that out, I need to know about x minus z. Is that divisible by 2 or not? And the answer is yes, because if I add these two equations here, I cancel the y's, and I get x minus z is equal to 2 times k plus m, and that is a multiple of 2. We've shown if x is congruent to y mod 2 and y is congruent to z mod 2, then actually x is congruent to z mod 2 as well. So this is a transitive relation. It has all three properties: reflexivity, symmetry, and transitivity. Therefore, it is our first equivalence relation. And of course, you'll notice, if you look at this, there's actually nothing special about the number 2. We've argued here that congruence modulo 2 is an equivalence relation, but the same argument would show that actually congruence modulo n is an equivalence relation for any positive integer n.